kinetic energy, intermolecular force, kinetic energy, intermolecular force, and kinetic energy, intermolecular force. So what we need to do is we need to add greater than or less than symbols to say, during this process, which one wins. So when ice melts to a liquid, which thing wins? Does the kinetic energy win, or does the intermolecular force wins when solid melts to a liquid? Kinetic energy wins. So I'm going to draw a greater than sign there for melting. So go ahead and finish your diagram with what you think happens. In each of these processes, what thing wins? Does kinetic energy win, or does intermolecular force win? Another minute, 15 minutes, and about 3 more concepts to go over. Oh, by the way, this is, like I said, the quickest unit in this whole year. Your unit test, it's going to be a small one, is Wednesday.
Oh, wow.
Yeah. We have activity, we have lab activity, worksheet, lab activity, test. Yes.
When's the last day we can take the test?
Fridays. If you aren't happy with your performance on the gases unit test, you are welcome to retake it up through a week from tomorrow.
Oh, yeah, like
Yeah. Normally it would be tomorrow, but no. Coronavirus. You need a little extra time.
It starts for everyone, right?
Yeah. Yeah.
Is sublimation just solid into gas?
That's exactly what it is. Yeah, sublimation is just solid into gas. We have been trained around water to think you have to go from solid to liquid to gas. A lot of chemicals don't do that. They just jump right to gas, and I'll show you why in a little bit. Yeah, we live in a water environment where we have to hit liquid first, but that's not necessarily the case everywhere else.
But
okay.
In those situations, would the solid go to liquid first then gas, or would it?
For waters, at our atmospheric pressure, yes, but that's not the case in other planets and other environments. Some chemicals skip over liquids entirely. Okay, so if in melting kinetic energy wins, what wins in freezing? Yeah, so in freezing, it is the intermolecular forces that are getting larger than the kinetic energy. When liquid water evaporates into a gas, what wins, the kinetic energy or the intermolecular force?
Kinetic energy.
The kinetic energy wins. And the opposite of evaporation is condensation. So during condensation, which one wins?
Intermolecular force.
Intermolecular forces are winning. And sublimation is usually explained with dry ice, that solid block of dry ice becoming gas. So when the solid dry ice is becoming gas, which one's winning? Kinetic energy is winning. And to make the dry ice, we deposit it goes through deposition, and to make those gas molecules stick together, which one has to win? Intermolecular force. Okay. Now, I'm going to erase these, but we're still going to use your diagram. Okay? Are we cool with this?
Yes.
Question?
Is there such things as solid nitrogen?
Yes. And I'll show you, hopefully, I hope we'll get to it. I'm spending a little more time bird walking than I wanted to, so I have a video about solid nitrogen, and I hope we'll get to it. Okay. Equilibrium. So you've seen balanced chemical equations. These are equilibrium equations. To melt, guys, look at this. To melt, you take some solid, add some heat, and you get liquid. Make sense? To melt, take some solid, add some heat, get liquid. But isn't the opposite also true? That to freeze, you take some liquid and you make a solid. But here's the crazy thing. By making your solid, you also have to release the heat. to take a liquid and create a solid, do you not have to pull heat out of it? The hardest part about this unit is realizing that we as humans, and especially you as teenagers, are egocentric. What does it mean to be egocentric? Self-centered. You're the universe. You're the universe and everything around it. So you have to think not about you, but about the system in front of you. Okay? What is the system doing? You are in most cases the environment. You are the surroundings. So when you hold a block of ice in your hand, it feels cold. Why does it feel cold? Because it's taking heat from you, the surroundings, and its heat is going in. So when something melts, it takes heat into the system. When something freezes, it gives heat out of the system. Does that make sense? Okay, if it doesn't, it will. Couple ground rules in writing heat. You never write plus cold, and you never subtract anything. In chemistry, you don't subtract, you only add. So you will never see minus heat, and you will never see plus cold. Okay? You never write cold, because cold is just less heat than we want, or less heat than we're comfortable with. So you never write plus cold, and you never write minus heat. You just write plus heat on the opposite side. So let me show you what I mean. To evaporate, you take a liquid and you add heat to get to a gas. That's evaporation. This one is evaporation. But condensation works the same way. In condensation, you have a gas and you are getting to a liquid. What side does heat go on? For condensation,
Liquid side.
it goes on the liquid side. Which is why, when you put your hand in a stream of steam, it hurts a lot. Because that steam is condensing on your hand, releasing a lot of heat to you, the environment. When gases condense into a liquid, they release the heat into the environment, which, if you're stupid, is your hand in the steam stream. Like, does it really? Oh, it does! Okay. So, the reason we call these equilibriums, where there are two things happening at the same time. At 0 degrees, guys, at 0 degrees, that block of ice is both melting and freezing. At 100 degrees, Celsius, that's important. At 100 degrees, that puddle of water is both evaporating and the gas is condensing. And I'm not going to do that with at dry ice, negative 75 degrees. Anyway, you get the idea. So it's called the dynamic equilibrium. Two processes happening at the same time.
So you know how you said at room temperature, a small amount of water has enough energy to evaporate? It would also go the other way, that a small amount of gas has strong enough intermolecular forces to turn into condense?
Yes. Yep. But then evaporating it. Gases are harder to see because they're everywhere. Light doesn't bounce off of them. Okay, does this stuff make sense? Can we move on? If you're ready to move on, give me a thumbs up. If you want to talk about some more, wave your hand around. Moving on. The Shelleys Principle is really cool. So the Shelleys Principle basically says this. Universes, systems, and everybody else like to be in equilibrium. You like to be in equilibrium. Okay? You like when your life is more or less stable, even though there's all sorts of crazy stuff going on. When you create a stress to throw something out of equilibrium, the system tries to get back to equilibrium. Okay? When you come home and you're like, Mom, I got stress in my life. You're like, let's try to do something to get back to equilibrium. So that's the Shelleys Principle. If you like book definitions, it is a system in equilibrium will change to resist stress to that equilibrium. My definition is, whatever you do to the EQ, I will undo to redo the EQ.
What?
Whatever you do to the equilibrium, I'm going to work to undo whatever you did. Whatever you do to the EQ, I will undo to redo the EQ. A system at equilibrium will resist stress to that equilibrium. Do you guys know the word inertia?
Inertia is a property of matter.
Inertia is a property of matter.
That's
Right.
Good job, guys.
So inertia is resistance to change. It's usually referred to as in like velocity. An object at rest will remain at rest until acted on by an outside force. An object in motion will remain in motion until acted by an outside force. But Le Chatelier's principle is chemical inertia. It resists change to a system. A system in equilibrium wants to stay in equilibrium. If you upset that, it will try to undo that stress. Let me show you what I mean. Imagine you got a pop can. Got your pop can? See the imaginary pop can? In the pop can is a bunch of carbon dioxide. If you pop the top and reduce the pressure, more gas is going to stay in the liquid phase or become in the gas phase. More gas is going to go to the gas phase. Which is why the third way I teach Le Chatelier's is up and over, down and to. Like this. When you pop the top to your can, you're reducing the pressure. That's going to force the equilibrium towards the vapor phase. More gas is going to end up in the vapor than in the liquid. Make sense? On the other hand, soda stream, guys, on the other hand, a soda stream rapidly increases the pressure, and that forces gas into the liquid. Up and over, down and to. That's Le Chatelier's principle. Okay. And we're going to focus on this a little bit with state changes, and a lot when we do the chemical equilibrium in a few weeks. 2 more concepts. Questions? No. Moving on. Okay. Vapor pressure. We talked about vapor pressure last time, so I don't want to spend too much time on it. But there is one piece of lingo you need to know. So again, liquids, that little particle, little bit of the particles at the end, liquids want to push their particles into the gas phase. That's where vapor pressure comes from. You remember the syringe? We did the syringe, and we removed the atmospheric pressure. What did the water in the syringe do? It boiled, right? Even in that warm temperature, it just boiled. Substances that have very low intermolecular forces are considered to be volatile. A volatile substance is something that has very low intermolecular forces. And because they have low intermolecular forces, they evaporate easily and have high vapor pressure and a bunch of other things, like they don't have very good cohesion. If you filled up your swimming pool full of alcohol and you jumped into it, not only one, would you sink to the bottom because density is a lot less than water, but you'd make a very small splash because there isn't a lot of cohesive forces. There's not a lot of water to get out of their way. And it would also be hard to swim in. You could swim in it a little bit because it does have a little bit, but you definitely wouldn't swim as fast as in normal water. You're like, come on, guy, gotta go. And the alcohol's like, I'm happy to get out of your way. I will just get out of your way.
So they're basically Canadian.
1 and 2. Okay. So
If it has a low intermolecular force, is it harder to freeze? Like I know in ethanol, it's
Yes.
really hard to freeze because of that.
yes, exactly right. Yeah. It would require a lower temperature to get the molecules to stick together. Yeah.
Is there a liquid with this density that like you just like give a black bond?
Besides, oh, almost certainly, yeah. Yeah, ethanol ethers would do that. Yeah, you would still, the density of, they're low enough that you would basically be walking across the bottom. Okay, last concept. I love this concept too. Okay, any questions about this before we move on? If you're ready to move on, give me a thumbs up. If you want to talk about it some more, wave your hand around. Wave your hand around? Okay, we're good. Okay. Phase diagrams. Phase diagrams are pretty cool graphs of temperature and pressure. We put the temperature on the x-axis and the pressure on the y-axis. This graph is in kilopascals, but we convert it to say 101 kilopascals is 1 atmosphere. So phase diagrams, we're going to have an activity tomorrow where we make a phase diagram, are graphs of temperature and pressure. And they work like this. What phase of matter do you have at 1 atmosphere pressure and 50 degrees? Liquid. Okay. What phase of matter do you have at 1 atmosphere pressure and 130 degrees? Vapor. What phase of matter do you have at half an atmosphere and 30 degrees? Liquid. By the way, what do you think the phase? What species do you think this is? what chemical do you think this is representing? It's water. Because at 1 atmosphere and 0 degrees, you go from liquid to solid or solid to liquid. At 1 atmosphere and 100 degrees, liquid or vapor, vapor to liquid. So in the phase diagram, if you have a specific temperature and pressure, you can know exactly what phase you're at. Anything on the line will be in equilibrium. So this is the boiling line. Anything on this line, you have both liquid and vapor at the same time. You have both boiling and condensing at the same time. This line, of course, is the melting line, and of course there's also a sublimation line. Right there.
So,
Yes?
at the triple point, would it be equilibrium from all three, or?
Yes. So the special point in a phase diagram is called the triple point. It's only a point, it's not a line. It's right there where all 3 zones meet, and at those all 3 zones, you get all 3 phases in a rolling equilibrium. And that's what I want to show you. So, the video is 7 minutes. We're probably not going to get to all 7 minutes, especially because of YouTube's commercials, but whatever. Sarah, will you press the silver button, please?